So, good morning, everyone, and welcome to this lecture. This is lecture number 4 in current electricity, and in today's class, we are going to discuss and understand Ohm's law and wind up this part so that we can move to the other parts. Now, before going on to discuss Ohm's law or the other things, we had seen the relation between drift velocity and current in the previous class. I is equal to NAEVD and current density is NE into VD. We all remember these relations? We had done some problems on that relations as well. Do we remember it? We had done some problems on it. Whether in those problems we had found out the relation between drift velocities, currents and all those things. Do we remember it, beta? Yes or no? Do we remember all those questions that we had done? Yes or no? Do we remember it, anyone? Do we remember it, anyone?
Sir.
We remember it?
Yes, sir.
Sure?
Yes, sir.
Okay, I was not getting any response, so I got I got confused. So, since we have done all this, let us now move on and see the next point. And the next point is this. What is the next point? We can write the next point as mean free path. Mean free path. Now, what do you mean by this mean free path? It is represented by the letter lambda. This is the average distance or you can say displacement of electron between two successive collisions. Now, whenever this electron is moving inside a conductor, you must understand, you must realize that this electron, there are a large number of electrons moving inside the metal and they are continuously colliding with each other. Do you understand this?
Yes, sir.
So they are colliding with each other, whatever distance it travels between two collisions is known as mean free path. Do we understand this?
Yes, sir.
Okay. Now, this is the mean free path. Then the next term that is going to come is known as relaxation time. Relaxation time. Now, what do you mean by relaxation time? Relaxation time is written by tau. It is the time between two collisions. Do we understand this? The time taken from one collision to the next collision. Time between two collisions is known as the relaxation time, and you can relate all these three terms and drift velocity or the velocity of electrons lambda by tau. You can also write drift velocity or the velocity of these electrons as lambda divided by tau. How much is the average distance they have traveled and what is the time between those collisions? Do we understand this, everyone? Is it clear to everyone? The
Yes, sir.
relation between velocity, the mean free path, and the drift velocity. One more term that comes in your exam sometimes is known as mobility. Mobility of electrons, it is denoted by the letter U. It is denoted by the letter U. Okay, if someone asks you the SI unit for mean free path, it is length only, so it is meters. The relaxation time, if you talk about the SI unit, it is seconds. Do we understand this? Because it is
Yes, sir.
time. Now, once you come into mobility, and you will have to remember the units and dimensions of these things because they might sometimes come. This mobility is defined as drift velocity per unit electric field. Drift velocity per unit electric field. So basically, your mu becomes drift velocity divided by E, where E is your electric field. Do we understand this? The SI unit becomes meter square per volt second. Not meter. Do we understand this? Do we understand this, what I've written?
Yes, sir.
What is the SI unit of mobility? It is drift velocity divided by electric field. Can you tell me what will be the SI unit coming? What is the SI unit of electric field? It is volt per meter, yes or no? And the SI unit of drift velocity is meter per second. So if I find out the SI unit for this, I wanted to I wanted you to find it out, but let me give you that. Meter square per volt second is the SI unit of mobility. Remember these things because they have been asked in your exam. I'll give you 2 minutes to note them down. Okay, so now we are done with writing. We'll move ahead and we will write one of the most important headings of this chapter, and that heading is known as Ohm's Law. Have you heard this Ohm's Law before? Have you heard Ohm's Law before? No one has heard about Ohm's law? Well,
Current is directly proportional to voltage, sir.
well done, sir. I'm happy that you have heard about it. Anyways, I was anyways going to tell you now. If I have to write it in complete description, I will write it in this way. If the physical conditions of conductor, when I say physical condition, length, area, temperature, all this remain same. If you have a conductor whose dimension, temperature, etc. are same, then the current flowing through the conductor is directly proportional to the potential difference. So I can write current flowing to the conductor is directly proportional to the potential difference. Remember, this V is the potential difference across the conductor. So if this is your conductor, this is your wire, this is your conductor, this is your wire. L is the length of the conductor or L is the length of the wire. We are talking about V, which is the potential difference across this conductor. And I is the current that is flowing through the conductor. Do we understand this, bacha? So current through the conductor, whatever current is flowing through the conductor is directly proportional to the potential difference applied across the conductor, or you can say V is equal to IR. V is equal to IR. Where what is I, what is R, what is V? Tell me what is I, what is I, what is R, what is V? Tell me fast. What is V? What is I? What is R? No one is going to tell me. Okay. V is the potential difference across the conductor. I is the current flowing through the conductor, and R is known as the resistance of the conductor. R is known as resistance of the conductor. V is equal to IR. R is known as resistance of the conductor. Now remember this Ohm's law, V is equal to IR is not a universal law. That means not every body is going to obey Ohm's law. Bodies which obey Ohm's law are known as ohmic bodies. They obey Ohm's law and therefore they are known as ohmic bodies. Basically, these ohmic bodies consist of your metals. Metals are the only bodies which follow this Ohm's law and they are known as ohmic bodies. Do we understand this? Do we understand this? I'm not getting any response. I'm very sad. Do we understand this?
Yes, sir.
Yes,
Please,
sir.
please let me know, beta. If I don't understand, I will not move able to move ahead. I don't know where you are, what you are doing. So please let me know. Please have that much courtesy to tell me that, sir, we have done this or we understand this. Please do that. Okay. Now, anybody which follows this Ohm's law, the graph between V and I would be a straight line. So this is how the graph between V and I will look like for a ohmic body, which is a conductor. If I plot V on the y-axis and if I plot I current on the x-axis, the tan theta or slope of this graph will give me the current. If V is plotted on the y-axis and I is plotted on the x-axis. But sometimes I is plotted on the y-axis and V is plotted on the x-axis. So you have to take angle with the y-axis. Do we understand what I'm telling you here?
Sir.
Okay. Now you can draw this graph at two different temperatures also, and you will see when you draw this graph at two different temperatures, you will see that the slope will become more. You can see this blue graph which is drawn at temperature T2 and this pink graph which is drawn at temperature T1 between V and I. The pink graph has more slope. So resistance during the pink graph is more. That means the temperature T1 is more. That means when temperature increases, when temperature increases, when temperature increases, the resistance of the wire also increases. Do we understand this? When temperature increases, resistance of the wire also increases. Do we understand this? Now I'll give you 2 minutes to note it down. Tell me once you are done. So now we move ahead and we understand that there are two types of resistor. One is known as ohmic, where we have resistance, the graph of V and R. V and I is a straight line, but there are other bodies whose graph is known as whose graph who do not follow Ohm's law, and they are known as non-ohmic resistors or non-ohmic substances. So their VI graph will not be a straight line. Do we understand this? The VI graph will not be a straight line. Those are known as non-ohmic resistors. Their graph could be like this. The graph could be like this. The graph could be like this. So they can have two types of resistances. One is known as static resistance, and the static resistance is simply V divided by I. One is known as dynamic resistance, which is change in voltage divided by change in current. And we will come across this dynamic resistance in the chapter on modern physics. In the chapter on modern physics, we will come across this dynamic resistance. So these are known as non-ohmic device. You may not have to draw the diagram, but there are conductors who do not obey Ohm's law. And what I am going to do now is to tell you those graphs. They may ask you these graphs. They may ask you these graphs. So what I will do, I will show you all these four graphs. You may not have to draw all these four graphs, but you will have to understand that these are the bodies who do not follow Ohm's law. And there are these four bodies who do not follow Ohm's law. And I will show you their graphs. Here, now, I hope you can see this graph. Tetrad valve, diode, semiconductor, and torch bulb. They do not obey Ohm's law, and therefore they are known as non-ohmic bodies or non-ohmic or non-linear conductors. I'll give you 2 minutes to write this down. So then we move ahead and we have understood that if VI graph is a straight line graph or V is equal to IR, that body is known as a ohmic conductor or a ohmic material. And we have understood that V by I is R. The next heading that we are going to write is the resistance. This is the next term that has come. Resistance. Resistance R of a conductor. What is the resistance R of a conductor? Yes. What is the resistance R of a conductor? Anyone who's going to tell me what is the resistance R of a conductor? Eh?
Which opposes the flow of current.
Yes. Resistance of the conductor is a property of conductor. Property of conductor by virtue of which it opposes what?
Flow of current.
The flow of current. What type of quantity is resistance? It's a scalar quantity. Do we understand this? The SI unit of resistance is ohm. Ohm. Or you can also write it as volt per ampere. Remember this SI unit and dimensions. Dimensions are m L square T minus 3 and A minus 2. Do not forget this. Dimension of resistance. This is a very important concept that you must remember. Have you noted this down, everyone?
Yes, sir.
Now,
Sir,
okay, the opposite or the reciprocal of resistance is known as conductance. So, since we have done resistance, we can also write conductance. Reciprocal of resistance is known as conductance. C, and this C will be equal to 1 by R. Do we understand this? Yes or no? No or yes?
Yes, sir.
Now, sometimes when, as I told you, sometimes what they do, instead of giving you the graph between between V and I, V on the y-axis and I on the x-axis, they might give you a graph where I is plotted on the x-axis and V is plotted on the I is plotted on the y-axis and V is plotted on the x-axis. Do you understand the difference between these two graphs? Yes or no? No, yes.
Yes, sir.
Now, if the graph is given between I and V, my dear friends, the tan theta of this graph, which will be I divided by V, that will give you the conductancy, and that will be the reciprocal of resistance. Do we understand this, everyone? Yes or no? No, yes.
Yes, sir.
I will give you 2 minutes to note this down. Now, once we understand this resistance, you must also understand the symbol of resistance. I forgot to to bring that symbol. So the symbol of resistance is like this. Do you know the symbol? Resistance R?
Yes, sir.
Know the symbol? So I forgot to give you the symbol. That is the electrical symbol of resistance. Now, sometimes we start thinking that conductor conducts current. So resistor is not a conductor. Resistor is a conductor. Every conductor has some resistance, and you must remember that every conductor is a resistor and every resistor has a resistance. Now, we are now going to move on the factors on which resistance depends on. So, dependence of resistance. What all the factors on which resistance of a conductor depends on? Now, let me just draw a conductor here just for academic purpose. Let us suppose that this is a conductor. This is the conductor that I have. Now, every conductor has a length L. Every conductor has a area A, area of cross section we call it. And every conductor is made up of some material. It will be made up of some material. It could be made up of copper. It could be made up of aluminum, gold, silver. Yes. Now may I ask, on what all factors does the resistance of a conductor depends on? What are the factors that you think on which the resistance of the conductor will depend on? Resistance will depend on what for a conductor? Yes. Resistance of the conductor, first of all, depends on the length of the conductor. I can write resistance of the conductor is directly proportional to the length. If a long conductor will have long, will have more resistance. Do we understand this? Yes or no? Similarly, a short conductor will have less resistance. Do we understand this? Yes or no? No or yes?
Yes, sir.
So that is the first point. The resistance of a conductor is directly proportional to its length. In fact, if I cut a conductor into n equal parts, the resistance of every part will become R by n, because the resistance is directly proportional to the length. Do we understand this first point? Yes or
Yes, sir.
no? No or yes?
Yes, sir.
First. Then the second point is area of the conductor. Now, you can see, you can understand that if area is more, there is more space, there could be more free electrons, and therefore, if there are more free electrons, the current will be more or resistance would be less. So I can say that resistance will be inversely proportional to the area. Do we understand this?
Yes, sir.
So resistance of the conductor will be inversely proportional to the area. That is point number 2. Point number 3, it depends on the material of the conductor. Resistance of the conductor depends on the material of the conductor. Resistance of the conductor depends on the material of the conductor. If it is copper, it will be different. If it is aluminum, it will be different. If it is gold, it would be different. If I put all these things together, I can write R is equal to rho L by A. The new term comes rho. New term comes rho. New terms come rho. What does A stand? What does L stand for here? What does L stand for here? What does L stand for here? No one knows it. L stands for the length of the conductor. A stands for area of the conductor, and rho is known as resistivity of the conductor. Rho is known as resistivity of the conductor, and it depends on what? Rho is known as the resistivity of the conductor, and it depends on material of the conductor and its temperature. At what temperature the conductor is. Rho depends on the material of the conductor and it depends on its temperature. Since rho depends on temperature, resistance R also depends on temperature. So the next term that you have to understand is the fourth term. The resistance depends on the temperature of the conductor. In fact, I can say resistance is directly proportional to temperature. If temperature increases, resistance increases. If temperature increases, resistance increases. Have you noted down till here?
No, sir.
Okay, then I'll give you 2 minutes to note it down. So, if I now give you the graph of dependence of resistance with temperature, the graph looks like this. The graph is like this. Here R naught. What are the things that you have to remember? R naught is the resistance at 0 degrees Celsius. RT is the resistance at T degree. RT is the resistance at T degrees Celsius. And I can write a very wonderful relation between this. RT will be equal to R naught into 1 plus alpha into T, where alpha is a constant which is known as the temperature coefficient of resistance. Alpha is known as temperature coefficient of resistance. Temperature coefficient of resistance, and you can find out the value of alpha. It will be RT minus R naught divided by R naught into the temperature T. Do we understand this? Yes or no? No, yes?
Yes, sir.
Okay. We can also write a formula. Resistance at temperature 1 divided by resistance at temperature 2 will be equal to 1 plus alpha into T1 divided by 1 plus alpha into T2. Do we understand how did I get this formula?
Yes, sir.
Resistance at temperature 1 will be R naught into 1 plus alpha into T1. Resistance at the second temperature will be equal to R naught into 1 plus alpha into T2. I can divide them. So these are the wonderful formulas that we have got. I'm going to highlight them in yellow. And these are the forms that you must remember and you must use. This is the first formula. This is the general formula. This is the general formula. This is the formula for alpha here. This is the formula for alpha here. And then the graph, if you can remember these things, you will do very nicely. One more thing has come here, which is resistivity, which we will see in the next class when we go and see the different types. We will cover resistivity and conductivity in the next class. So we will cover all these points. I hope everyone has understood what we have done in today's class. Yes or no?
Yes, sir.
Everyone has noted down everything. Yes or no?
Completed,
No,
sir.
sir.
Everyone understood this. These are very important formulae beta because questions on this are very likely to come. Questions on what are non-ohmic resistors, questions on how does resistance vary. We will be doing a lot of questions on this. Don't worry about that. I'll give you one day. I mean, so tomorrow is Sunday, you have an off. So you can go back and when you come to the class in the next class, please go through all these formulas. Can you do that for me?
Yes, sir.
Then we'll meet in the next class on Monday. Wishing you a very Merry Christmas. I forgot it. I mean, it's a last class just reminded me that today is 24th. I lose track of all dates and days. So wishing you a very Merry Christmas and enjoy your festivities, but do your work because that is your karma. Take care. God bless you all. Bye bye.
Bye, sir. Thank you, sir.